Welcome to the video on factors that affect enzyme action. Today we're going to discuss 4 factors that affect enzyme action, or the rate at which reactions or enzymatic reactions occur. So the first factor we're going to look at temperature. And in all these graphs, you're going to see the factor that we're looking at the bottom, okay, and the rate of reaction on the y-axis. And again, there's no units here, so this is sort of a bad graph. These were different than the graphs that we looked at, that was Monday, because on this axis we had time, and on this axis we had amount of product. So here, what they're doing is they're doing the reaction. Let's say they're doing the reaction of turning. I apologize, I have to reset what I just said because I was distracted by hyenas, so I forgot what I just said. In the graphs that we were looking at on Monday, we were looking at time on the x-axis, okay, and product on the y-axis, okay. So what we're doing here is, let's say we're doing a reaction where we're turning a disaccharide. So remember, disaccharides have 2 rings. There's my disaccharide with 2 rings, or horrible drawing. And we're breaking it into 2 monosaccharides. Here's my rings. Don't make fun of my drawings that aren't rings. Okay, so we're saying we're going to do this reaction at many different temperatures, and we're going to measure the product over time, and then that's the rate, and we're going to graph it several times. So here, they did the reaction at 10 degrees, they did the reaction at 20 degrees, 30 degrees, 40 degrees, 50 degrees, and 60 degrees, and they calculated the rate at each temperature by dividing the amount of product produced divided by the time. Okay, now on this slide, I need you to really write what I say. There's not a lot of text on this slide, so you really need to annotate this slide. So if we're looking at the relationship between how fast the reaction occurs and temperature, we'll see and it's very, very cold, the reaction is slow. Okay, and the reason that is that when temperature is low, the molecules in general move slowly. So then it's harder for the enzyme to find the substrate. Now, as the temperature increases, okay, the molecules begin to move faster, and then the enzyme can find the substrate more quickly and place it in the active site. Here is the optimum temperature, okay? In terms of, this is when the molecules are moving the fastest without denaturing, so that they can find the substrate the quickest. However, after the optimum temperature, okay, some of the enzymes, okay, begin to denature, and as you continuously increase the temperature, more and more of the enzymes denature. Okay, now, just so that we remember what denaturing means, okay, so denaturing, or denaturization, is when enzymes lose their 3D shape or they unfold. Okay, and it's important to remember, okay, that you're not breaking peptide bonds. Okay, the high temperatures disrupt the intermolecular forces, the hydrogen bonds, the ionic interactions, the disulfide bridges, the hydrophobic interactions, which put the amino acids in the middle of the protein. The high temperature interrupts those interactions, which make the enzyme lose its shape. Okay, but the primary structure, or the peptide bonds, are not interrupted. So here we see a enzyme with an active site here. And in this case, it says lower pH, but let's say we're increasing the temperature. You'll see what breaks in this case, what's causing to break, is the disulfide bridges, and other parts of the protein also unfold, so maybe some of the hydrogen bonds break, okay? And now, the enzyme no longer has an active site, okay? And as a result, the substrate can no longer fit in the active site, or the active site is not provided, and the reaction doesn't occur. Now, again, this doesn't happen immediately. All the enzymes don't denature immediately. As the temperature continues to increase, more and more of the enzymes denature. Okay, now we have pH. pH, as I pause, each enzyme has a particular pH that it works the best at, where its structure is the most stable. Okay, most enzymes have a pH that they're the most stable between 6 and 8, some a little lower. But there is an enzyme in our stomach called pepsin, and pepsin breaks down protein in our stomach, and it actually has an optimum pH of 2. what that means, okay, is at the optimum pH of 2, that the structure of the enzyme is the most stable, or the active site at that point is the most stable, and therefore the reaction can occur the fastest. Sort of here we see a graph. So pepsin, which is located in the stomach, has an optimum pH of around 2. pH is below that, or above that, cause the active site to not be as correct of a shape, and therefore the rate of the reaction decreases. Trypsin, which is actually also, which is in the small intestines and breaks down proteins even smaller actually, has an optimum pH of about 8, and you'll see the same thing. pH is below 8, or pH is above 8. The enzyme is not the optimum shape to catalyze the reaction. Another way of saying this is that below or above the optimum pH, the substrate, the shape is slightly different, and the substrate is not as attracted or doesn't have that great affinity for the active site. Okay, now, so far we looked at the effect of pH and temperature. And one thing that I actually want to go back and look at is that in this graph, let's say this is the graph of a denaturization of a enzyme because of a change in pH, which it could be as well. Notice when we lower the pH, remember when you lower the pH, that means there's more H plus in the environment. And if you're looking at what's happening as the bell rings, if you're looking at what's happening to those enzymes, those H's are actually going onto the S's. And breaking the disulfide bridges, causing the enzyme to denature. So here, and specifically, we're sort of seeing the greater H plus in the environment breaks the disulfide bridges, therefore causing the enzyme to unfold. The next factor we have to look at is the amount of enzyme, or the enzyme concentration. Okay, now, so this is saying we're doing the reaction of our disaccharide, so remember our disaccharide to our monosaccharide, and we're increasing the amount of enzyme that is doing that reaction, okay? As you increase the amount of enzyme, as you go this way, okay, the reaction occurs faster and faster and faster and faster and faster and faster, okay? And the reason why that is that there's more enzymes, okay, available, okay? So more enzymes can do the reaction. Okay, now this graph is assuming, okay, that there's an excess amount of substrate, which there usually is. Okay, now if there wasn't a large excess amount of substrate, think for a second, how would this graph change? If this wasn't true, if there wasn't a large excess amount of substrate, okay, which usually there's more substrate compared to enzyme, think about how this graph would change. Okay, so think about it, right? And the answer is that this graph would then level off. Right? The rate wouldn't be able to go any faster, right? We increase the amount of enzyme, and the reaction goes faster and faster and faster. The rate increases. We can make more monosaccharides per minute. But all of a sudden, if we run out of substrates, assuming it's not an excess, then the reaction won't be able to go any faster. Because we're running out of substrate, so the rate will level off. And in fact, if we run out of substrate, the rate will actually go down to 0, right? If there's no substrate at all, then we won't be able to do the reaction at all. The reaction will stop completely. Okay, our last factor that we have to look at is, let's say we're looking at substrate concentration. So how does increasing the substrate, so remember our substrate in sort of our scenario is a disaccharide and we're breaking it into a monosaccharide. So what we're doing in this scenario is that we're doing the reaction several times, and every time we're doing it with more disaccharides. So maybe here where we have 1 gram of disaccharides, and then we do the reaction with 2 grams, 3 grams of disaccharide, 4 grams of disaccharides. Remember, disaccharide is the substrate that we're breaking down. And we'll notice here with the rate of the reaction, as we increase the amount of substrate, the reaction occurs faster. And again, the reason why that is that there's more substrate, so it's easier for the enzyme to find the substrates. Again, I'll say that again. As you increase the amount of substrate concentration, or the amount of disaccharides in this case, okay, because there's more substrates, it's easier for the enzymes to find to find the substrates. Okay, but at a certain point, okay, since there's usually much more substrate than enzyme, all the enzymes are working. And there are substrates just waiting. Okay, and the reaction can't go any faster. So the rate, well, it doesn't go to zero. This doesn't mean it goes to zero. It's just that the rate can't increase anymore. The maximum number of enzymes are working. So the reaction is occurring as fast as it can. And this is called the saturation point, when the rate of the reaction stops increasing. I'm going to talk, if you understand this, you can sort of skip this part, but I'm going to talk about a scenario here to see if you understand this better. So let's say the cashiers are you're at Walmart, and the cashiers are enzymes, and the job that they catalyze is that they check out people. Okay? And let's say there's one cashier and 100 people that need to check out. That's going to go very, very, very slowly. Okay? But as you add more cashiers, okay, the time that the people will be waiting, okay, or more people will be processed out of the store or be wrung out quicker as you add more cashiers. Okay? But at some point, let's say there's 10 machines, okay? At some point, there'll be no more cashiers, and people will still be waiting, okay? So maybe now there's 10 registers, and then now before there was only one working, and now there's 10, okay? At that point, even if you increase the substrate, even if there's like now 1,000 people, okay, that reaction can't go any faster because all the enzymes or all the cashiers or all the machines, or in this case, are occupied. So the reaction doesn't stop, okay? It's just that the reaction can't go any faster. All the cashiers or all the enzymes are occupied. So this slide, which is sort of a summary, summarizes the sort of different effect between enzyme concentration and substrate concentration. So you see what enzyme concentration, as long as the substrate is in excess, as you increase the amount of enzyme, the rate of reaction occurs faster and faster and faster and faster. However, with substrate, okay, as you increase the amount of substrate, the reaction occurs faster. But then at some point, since there's usually much less enzyme than substrate, all the enzymes are working and the rate levels off and the reaction can't go any faster. So these sort of compare the two. We're going to be doing a lab, I think next week's, whenever we have class, the first day we have class next week, where we look at this. We're going to measure the effect. We're going to change the amount of substrate and see if we get a graph like this. We're going to talk about that lab and sort of how we're going to do that lab next class. All right, so I will see you guys on Thursday. Have a good half day.